Again, apologies from Ashley. Ashley's just started a new job and she had an extremely important meeting scheduled just a couple of days ago that she was required to attend. So you know how that goes anyway, and particularly with your first job. So she sends her regrets, and I want to summarize the work here and also upcoming ones with Ben and myself on 2 additional talks that address a lot of the questions about impact crater formation and evolution on Mars in particular. And the key theme here is what is in fact the degradation state of early pre-Noachian, primarily Noachian and late Noachian, early Hesperian craters, and what can they tell us about the climate? What effects do the craters have on the climate? What climate effects do we see on the craters themselves? So initially, I want to talk about the large impact basin-related climate and surface effects, and in particular use Argyre as an example. So the key points here is there's been a lot of work by Teresa Segura and others, 2002, 2008, Owen Toon, and also Ashley and I have a paper in MAPS 2018 that came out of a previous cratering conference. And basically the question is, what do large basin impact events do to the global climate on Mars, to the atmosphere on Mars? Well, all of these works indeed come up to pretty much the same conclusions. There's difference in terms of time, and of course with increased understanding of hydrocode models, et cetera, there's been a lot more understanding of actually the details and the durations of different parts of these events. But a key point is that there are 3 fundamental things. There's a transient high atmosphere surface temperature and surface temperatures that derive after the event. This is, of course, well known. We've talked about this with impact melt and other things, but it's really critical in the atmosphere. And mostly yesterday, we were talking about the moon, and we didn't have to worry about that. There was some great discussion about, is there a transient atmosphere? But generally, it's not the same as Mars at all. And I'll talk about that in the 3rd talk. So one thing that happens here, too, there's deposition of a hot spherular layer. This is what we see on the Earth. And the predictions are that the same thing should happen on Mars because we're, in fact, vaporizing silicates into the atmosphere. And then, in addition, there's something else that most people haven't thought a lot about. The authors in the lower right-hand corner, Segura and our colleagues in Toon and colleagues have in fact, a transient phase of intense hot rainfall. In these earlier papers, this was generally attributed to, in fact, what caused the valley networks. But indeed, later work by us and others have shown that, in fact, that's not the case, that, in fact, they're separated in time. So the bottom line is, though, that a period of intense hot rainfall, and that's really important from a crater degradation and geomorphological point of view. So what Ashley has been able to do, and we also have another paper, 2 other papers actually, Martin Turbet and colleagues at LMD and in Paris and elsewhere, we combine hydrodynamic codes modeling as well as atmospheric modeling and geological observations. So all of these papers on the right, Colombo and Head and Turbet et al. Are really relevant here. So what we're seeing here is, in fact, the timeline, okay? Basin formation and its environmental aftermath. Essentially, we have the events here, and then we have the timeline here. And believe me, I could talk about this a long time. It's really exciting and interesting, but let me just summarize it into these several phases. The intense impact, of course, forms a silicate vapor plume, and then it expands and cools. So when the silicate vapor expands and cools, it undergoes condensation and then condensate deposition. Following that, the water vapor, as the temperature of the cloud essentially decreases, water vapor condensation occurs and results in global rainfall, global hot rainfall, okay? This produces an intense hydrological cycle. And if you look here, the event happens obviously fast because there's a hypervelocity impact, but these events here occur over the course of months to years in terms of the evolution of the plume and its deposition, and then the water vapor you can see here. After a few years, you start undergoing this intense hydrological cycle that lasts hundreds of years. Now, this is really important because it has amazing effects on mineralogy. You know, we sit here and try to understand phyllosilicates and where they came from. Well, this is a really good candidate because it has incredibly high temperatures, has a hell of a lot of water, and in fact, that's all mixed together and actually can fall to the ground penetrate, melt any snow and ice on the ground, penetrate into the substrate, and in fact alter the surface in terms of essentially ambient minerals to in fact phyllosilicates. So when we think about this, the large basins formed in the early to middle Noachian. This is why it's really important. Of course, in the pre-Noachian, there were a large number of basins, including the northern lowland basin, the Borealis Basin, which formed the dichotomy boundary. But in the early to middle Noachian here, three big basins formed: the Hellas Basin, the Isidis Basin, and the Argyre Basin. This is a timeline that Kayla and I put together when we were trying to understand the evolution of these early periods, and it's a subset of that. So the formation of the larger basin, in fact, is really contemporaneous with the surface aqueous alteration of the phyllosilicates, and clearly comes before the sulfates and evaporites that are in the late Noachian and early Asperian. So this is really interesting because, in fact, there could easily be a cause and effect. Clearly, we have a lot of degradation going on here, and we may have chemical alteration as well. Now, of course, one of the things we've been able to show here, in contrast to the earlier work, is that the ages of these are very different than the age of the valley network. Fassett et al. 2008 mapped 30-odd, or more than that actually, valley networks and showed that they were, in fact, late Noachian and early Asperian, and the same is true for the open and closed basin lakes and that activity as well. So not only is this dominating in the early periods, but it's also contemporaneous with where we think the phyllosilicates were formed. Now these are really important because these three basins, okay, essentially Hellas shown here, Isidis shown here, and Argyre shown here, are in fact really big basins, and they will have a major, major effect. Now we're going to be able to test this somewhat because, as you all know, the Perseverance rover is scheduled to go to this area in here, Jezero crater, and that should have deposits, in fact, of the Isidis Basin deposition. So if we think about this, let's talk about Argyre first and come back to Isidis. But Argyre is the youngest of the three basins. And if we take a look at the characteristics of this, we have analyzed, and we're in the process of mapping out the details of the structure of these basins, in particular looking at the degradation of the basin morphology, as well as the degradation of surrounding craters that have been influenced by the basin and subsequent activity. And basically, since this is one of the youngest basins, it should have had the largest effect on the surrounding regions, et cetera. And in fact, we should see a lot of evidence for modification if, in fact, the basins cause modification. If we take a look at the Oriental Basin, for example, which is about the same age range as the Argyre Basin, it has a distinct raised rim, significantly crisp and structures, et cetera, radial textured ejecta, secondary crater clusters around it, et cetera, all of which are really distinctive. We had a great time talking about that yesterday, and I'll pick up a little bit on that later on today. So that's really important for a lunar case, okay? But we're on Mars now, and not only do we have an atmosphere and a climate, so to speak, but we also have, in fact, this problem with impact ejecta and the formation of these effects, not just on the substrate, but also in the atmosphere, et cetera. So in comparison to Oriental, Argyre has really experienced abundant erosion that cannot be fully attributed to background erosive activity. The subsequent climate, et cetera, basically is, we find, to be insufficient to really cause the erosion that would make it disappear. That is to say, the post-basin after several hundreds of years, et cetera. So for example, we don't see any evidence at all for significant secondary craters. We don't see radially textured ejecta around Argyre. And all of these areas in the interior here have been modified. Some of this is clearly related to later ages. There's some valley networks and possibly even some glaciation in here. But the bottom line is that the general morphology is very different than what we would expect from a relatively fresher basin. And it is not all due to subsequent activity. So we think that a culprit for that could easily be, in fact, this late stage modification from this intense fluvial and hydrological cycle. So again, to come back to this, this hydrological cycle could in fact last for hundreds of years, and the effects are really quite remarkable. We've modeled these as well. This is in in the papers that I mentioned, the Palumbo and Head 2016-17, particularly the one in PNAS. And let's take a quick look at the basin scale impact event aftermath. So what happens indeed is in this phase, we get a global rainfall, which in fact is precipitation of these hot rains. And I divided up this into proximal near the basin and distal away from the basin. The bottom line is you get both effects because it's fairly global effect, in fact. And indeed, you get a hot silicate condensate layer. The rain falls partly after it definitely falls after the hot silicate condensate layer. And so indeed, this could easily be olivine excavated from deep within the crust or mantle, in fact, that in fact precipitates out as spherules and then gets altered, if you will, from, in fact, the precipitation of the hot rains. So the condensate layer formed of olivine-rich spheres would, in fact, be mixed with basin ejecta here. It would be on top of that, and then it's altered by the surface activity. So basically, the stratigraphic column might be excavated low calcium pyroxene-rich crustal blocks. Essentially, hot condensate would alter the FEMG smectites locally to kaolinite, alumina-rich clays. And then we would see the condensate layer formed of olivine-rich spherules, potentially rheomorphic flows of this as it was deposited. And then the hot rains partly alter the olivine to Mg carbonate as they come down on top. And then a global rainfall partly erodes these deposits as well. So we think this is very similar to the kinds of things that Bethany Ellman and Jack Mustard have mapped in the Isidis Basin deposits in the area surrounding these. And we think that if the Perseverance rover can get out of Jezero crater and go to the midway point, it's quite likely that it'll be sampling some of these deposits. So this is very exciting because it's a hypothesis that has some predictions here, and we think these can be tested on the Perseverance rover. Also, any of the sediments within Perseverance rover domain within Jezero crater will also be products of the erosion of these layers and deposition of them by the valley networks into the deltas that Perseverance will land at the base of. So the key points are that there is, in fact, transient high atmospheric and surface temperatures, hundreds of Kelvin above ambient, okay? Deposition of hot spherular layers could be as much as 30 meters thick, and a transient phase of intense hot rainfall. And these are really intense rainfalls. This is equivalent to sort of tropical rainforest types of activity, 2.6 meters per year. And this should serve to cause a lot of surface alteration, not just for the phyllosilicates, but also for the Mg-rich silicate clays and others, kaolinites, et cetera. And so we think this is going to be a really great place to test in the Perseverance rover area. Basin scale impacts, we should consider these in early Martian climate and hydrological cycle, and the post-impact effects, just post-impact effects, the rains, et cetera, are really likely to contribute to making smooth plains, degrading craters over the planet as a whole. And this is almost instantaneous, may have lasted hundreds of years, but that's nothing in geological time, and also a very big factor in aqueous alteration. You've got water, you've got hot temperatures, and you've got rainfall and an intense hydrological cycle to mix all these together. So the good news is that the Argyre-related units should be preserved at or near the surface, and these units should be identifiable at both the rover and orbital scale. So basically, we're trying to, again, think about the ways in which this has altered the surface and, in fact, altered these as a function of time. And this will be a component into our consideration of the general characteristics of Noachian crater degradation that I'll talk about in a later talk. Thank you very much.
Thank you, Jim. Much appreciated. I will now open the virtual floor to questions.
All right, there are a couple. First is from Bill McKinnon. Are you talking about a silicate vapor atmosphere or spherules formed by vapor condensation during the impact, which is a prompt effect as in the Archean spherule beds?
Yes, the latter, Bill.
Okay. That was a short answer. Sean Gulick, how is the temperature difference of the precipitation maintained? In other words, why is it still hot? And how hot is hot?
Okay, hi, Sean. So basically, we're talking here, how hot is hot? I think we're talking 1600 K. And let's see, I should have that on one of those slides, but not. Let's see, so the vapor expansion and condensation, let's see, you were asking, what was explicitly you were asking about that? Sorry for that.
How is the temperature difference of the precipitation maintained? In other words, why is it still hot?
Yeah, well, okay, so it's falling through the vapor cloud. The vapor cloud is expanding, and it's cooling to cause condensation. But then those nucleated silicates are obviously descending to the surface, and so the cloud is still, it's because it's over 1,000 Kelvin. It still hasn't cooled to anything near ambient conditions, and that's why not only are the silicates still hot, but also that it's very hot rainfall when the temperature decreases sufficiently to cause the condensation and precipitation of water. I hope that answers your question, Sean.
If it doesn't, let me know in the chat. Bill McKinnon he says yes, that's helpful. Bill McKinnon has, I'm not sure if this is a second question or more of a comment. He says, how much ice in the stratigraphic column to be vaporized by the impact, ? But then he says, oh, I see, the whole hydrosphere gets ultimately vaporized. Maybe you want to comment on that, or I can move to the next one.
Well, I think that, Bill, it's an interesting question. One of the issues that I'll talk about in the later talk is whether the surface of Mars at this time was in fact cold and icy or warm and wet. So those two scenarios are quite different from a geological standpoint. Whether you have an ambient, essentially rainfall related, rain splash dominated diffusional weathering regime, or whether or not you have the southern uplands covered with snow and ice due to essentially the adiabatic cooling effect and the deposition of most of the volatiles of snow and ice. So any impact is going to face one of those two fates, probably, okay, projectile into those. But the bottom line is that I think either one has whatever the water budget is there. If it's on the surface in the form of snow and ice, it's probably not more than, based on the water budget, probably not more than tens, I would say hundreds to maybe several hundreds of meters thick. And indeed, if it's a warm and wet scenario, then you have a hydrological, essentially a water table, and essentially a crust that is dominated by groundwater. So either one of them would probably, all that water would be vaporized in the target region and the nearby and the ejecta. And then when the ejecta came down, that would be when the story might be different. You might still have remaining thick ice in parts as the hot ejecta came down, the spherical layer, and obviously that would be added to the intense hydrological cycle, if any were to survive the blast wave and the initial deposition of hot ejecta.
Bill responded by saying, I thought you were talking about the surface temperature globally being elevated by hundreds of Kelvin.
That's correct.
Okay.
So yes, so I was trying to, I thought a part of your question was, what would be the fate of any sort of, under different conditions, snow and ice, or essentially a groundwater dominant regime. So both of those, basically, you could have these two different ones, but the bottom line would be that the event is so intense, it would probably not distinguish between the two modes of occurrence of the water.
Okay, two more questions at the moment. One is from, pronouncing your name wrong, I'm sure, Denise. I'm not going to try the last name. Although the atmosphere is thin on Mars, why didn't the existing surface shapes, such as coastal lines and dunes, disappear? Is it just the atmosphere that keeps these surface shapes alive? Is that enough? What other factors could there be? Can we say that the story of the atmosphere is determined by these big basins?
This is a good question. I think that the things you refer to, like oceanic shorelines that have been mapped and purported to exist around the northern up, these are all younger. Okay, so these are either, there's two possible oceans that have been proposed. One of them is late Noachian, the other one is late Hesperian, and so both of those are younger than what we're talking about here. This is definitely early to early middle Hesperian. Early to early middle Noachian, and so that, basically all of those kinds of features that you're talking about occur afterwards, and that's not a problem. Anything that occurred before that is likely to be severely affected, and I think a lot of the intercrater plains and highly degraded craters that we see on ancient Mars are absolutely related to these kinds of events, and that's what we're trying to map out in our more detailed view to test that idea, test the model. And so far, we see no secondaries that we've been able to identify from most of these basins. And secondly, the radial ejecta is also missing. And so the other part of your question is that, Vickery and Meloche had papers earlier. The basins can be large enough so that, in fact, you could, in fact, lose a lot of the atmosphere from the impact event itself. Most of the simulations that we've done would suggest that you retain a lot of the atmosphere here, a significant amount of the atmosphere with these three bodies. That's in the Turbay et al. Paper. But things like the North Polar Basin and larger basins than these here that occurred in the pre-Noachian, I think is a very good candidate for just simply getting rid of the primary atmosphere. And, so that's a signal we should definitely look for. It's a really good point for everybody to think about that you made, because, there's this issue about what is the primary atmosphere, what is the secondary atmosphere, and how do you go from one to the other? And maybe you have full stop and you start over with a secondary atmosphere at some of these pre-Noachian big basins.
All right, and we have another question from Anya Lusiak. Are you saying that the silicate vapor cloud would hang out in the atmosphere for years, or did she misunderstand something?
No. I may have, to quote one of my favorite earlier presidents, Ronald Reagan, I may have misspoke on that. That is the intense rainfall and hydrological cycle is what lasts for the long period of time. The vapor plume is, that's over in hours and days, basically. To weeks, I would say, yeah.
Okay, and for the moment, those are all of the questions in the chat.
Thank you. Does anyone have any other questions?
I'll ask one that's kind of just extended idea. How do you think this would extend to, say, like Venus or Titan, other surfaces with significant atmospheres?
I think these are the kind of effects you can. I mean, the physics they're not simple, but they're pretty straightforward. It's sort of like you have a sine. Okay, is it going to be the sign is not negative. Let's see, that's not a very good way to put that. I would say any planet with an atmosphere, including the Earth, as Bill McKinnon was pointing out, these spheroidal layers are all over the place in the early history of the Earth and the Archean, et cetera. And they derive from essentially the same kind of thing. And Sean Gulick, I'm sure, is seeing these types of things and in Chicxulub and other types of activities, impact events. Basically, can you repeat that question? Sorry, I had a momentary distraction from the side here.
I was just talking about extending it to places like Venus or Titan.
Yeah, so I would absolutely. The trouble is, like, for example, on Venus, we don't know what the earliest history looks like. Okay, so for example, the geological record on Venus today is largely, as Bill McKinnon has dated, in the less than 1 billion years for the average age of the surface, and So there are no events of the basin scale, of that basin scale anyway, that are left on the surface. But again, what's the evolution due to? What is it on Earth? I mean, I think something like this would have a serious influence on the early Earth. We see the spheroidal layers; those may be just later basins and craters. And again, what initiated plate tectonics? Did life start and have a fit and start kind of activity? These are all really good questions, but I think the pioneering work of Segura and her colleagues and Owen Toon and his colleagues, really set the stage for understanding this. And I think there's a lot to be learned, but these are things we all have to take seriously in the early history of all the planets with atmospheres. And maybe, in fact, one might think in exoplanets, whether or not you might have a primary atmosphere that was, in fact, blown off by one of these events and then didn't come back. Maybe the interior was insufficient to really generate the volcanic activity that might lead to a secondary atmosphere. So I think exoplanets are also an amazing laboratory for the study of this type of process.